So we also want to characterize just sort of the force displacement response of the bridge, both monotonically and cyclically. So let's open up the last one and modify it according to so this should be the, remember how we had to rotate it, right? And the other way. So looks like X and Z if I want to look at them. So view, set display options. View, set 3D view, X, Z. Aperture I'll set as 0, so it's not respectable. So that's how our bridge was, right, at the end. We ran an earthquake through it. So what I want to try right now is, instead of running an earthquake, I won't run that again because it takes a while. But what we'll do is unlock it. And then I want to grab the bridge, let's say at this node here, and pull on it to the right. First we'll just do monotonic. I'm just going to push on it. It's a pushover type of analysis. I'm going to run it as a time history analysis. In order to do that, we could either push on it, pull on it here, or we could do it here. Where do you guys want? Where do you prefer? You're going to grab on it and pull on it. What? Toyan, where do you want to pull on it?
At the end.
Okay, you hear that? So right here at this end, we're going to grab the bridge there and just pull it to the right. So that's in the, looking at this, the X direction. So we're doing displacement control. We have plastic hinges. We have plastic hinges at the bottom and top, right? These, this, and this. At least that's the way we remember this look. So yes, plastic hinge there, and
That's only the bottom fourth of the column.
say that again?
Isn't
Oh,
it?
that's right. Because here's another element here, right? So this one's at the top. Okay. So that's correct. So we have 1, 2, 3, 4, 5. There's not one at the bottom here because it's pinned at the bottom. Now, what we're going to have to do is say, it's sort of a series of events to do a pullover analysis in this way. So what we're going to do is first click onto this joint and say, let's first define a load pattern and just call it pull that. Add new load pattern. Oh no. Let's see. Pull. I don't want it to say dead. Remember other. Say modify. Okay. So say okay. And then I click on the joint. Okay. Click on it. Okay. 1 point selected. And then I'm just going to say assign joint loads displacement. Under the load pattern, I want to put it under pull. We're in kips and feet units. I'm going to apply 1 foot in the X direction. Say okay. Now, how much displacement did we have from the earthquake load? About 1/2 foot.
0.6 feet.
So a foot's reasonable. Let's see if that's enough. We got plastic hinge in the end of the column, right? We looked at the result. So we'll pull it 1 foot. So we want to amplify or multiply this on the scale back. So now let's say define load case. So there's a nonlinear direct time integration. That's an earthquake. We'll define a different one, okay? We call that earthquake time history. So add a new load case. Go over here and we're going to say time history analysis, direct integration, and nonlinear. So it's going to be a nonlinear analysis, but the time history will be grabbing the bridge and over a certain amount of time pulling on it slowly. And then so we'll call this, in some cases I'm saying pull, in some cases push, but I'm calling it push over, but really we're pulling on it, right? We're moving it from the end. load pattern. It's a load. It's not dead, it's pull. That's what we call that load pattern. Function file, I'll say ramp time history, and then we'll go and look at that, because we're not going to want to pull it in 1 second, because it has inertial effects, and it would be like grabbing a real bridge and loading it in 1 second. It would be huge acceleration. And the scale factor right now is 1, right? So I say add. So that means it'll go actually 1 foot, because we said 1 foot. It'll load it to 1. If I put a scale factor of 4, it'll go to 4 feet. So right now we're just doing a monotonic, and then we're going to cycle it and see how the bridge responds. The damping level, let's go over here and look. That here. I'm just going to put in my period, a large value, 0.5. I want to dampen out any vibrations that happen when we're pulling on the structure. I would use 0.5 in a dynamic analysis. It's just a quasi-static. Okay. Okay, let's see. So ramp time history, let's say okay, and then go look at define functions. Time history functions, ramp time history, if I look at that, it's loading, see over 1 second, I don't want that. So we'll create a new one and say user define, add new function. And so at 0, it's 0. Let's say at 10 seconds is 1, right? So the magnitude of this function, full time history, I'll call it. And say add to that, so that's what it looks like. If you wanted to go further, I'll keep it at 1 and say add. So what happens is at 0, the function value is 0. At 10, it increases linear. At 10 seconds, it's equal to 1. So it'll be multiplying this by whatever we did, and we have 1 foot. Right? So at 10 seconds, it will move at 1 foot. And then at 15, it's still 1 foot, and then longer. And then it continues again. So say okay. Now I'm going to go back, define my load cases. This is my pushover, right? Modify it. Right here, instead of ramp time history, I want to change that to pull time history that we just created. I'll say modify, and then it shows it here. Is that clear? Okay. 100 increments at 0.1 seconds, so that's going to load it over 10 seconds. So at the end of 10 seconds, it's loaded for 1 foot of displacement. Okay.
Excuse me. Damping is entered here 0.5. Is it 50% or?
Yeah, it was 50%. That's very large, a huge amount of damping.
Oh.
I'm trying to eliminate any vibrations because we're just pulling it slowly. And the actual dynamic earthquake motion, you want a very small number, then at 0.02, which is 2%. Okay, so will this run? Have we done everything right, or is there something wrong? Okay, let's save it and run it. Let's make sure we run the right one. I don't want to stand here for half an hour. This should go pretty fast. So run analysis. Under that, I'm going to say pull and push over both need to be run. This is the earthquake analysis. I'm going to say don't run that one. And the modal we don't need to run either now. So hopefully it just runs these two. The pushover is a time history analysis where we're pulling on it. And the word pull, that's just that analysis of a single 1 foot displacement. It needs both of those. So let's say run here. It's almost done, right? It says it's done. We'll see if it's done. Okay. This is pull. I right click, everything's 0. Okay? And if I go to pushover analysis, and I go to, let's say, 5 seconds, and I right click, everything's 0. right click over here. All the displacements, all the rotations are 0. Let's go to 10 seconds. Still 0. Okay, so I anticipated that, but you didn't. What's wrong? Why is it not moving? When you do a pushover analysis, when you do something in displacement control like this in SAP, we're not in force control. I'm not applying a force. I'm applying a displacement. To apply a displacement in SAP, you're actually moving the reaction point. So you take the reaction, the structure is connected to the reaction, and you pull it. So that means that there has to be a reaction in that direction, which there isn't. Right? It's a roller. So I give it a reaction at the point that Toyen wanted us to pull on it, and then it will move it. So right now, it can't move it. So now let's unlock it. Go back over here to that same joint. Everything else is the same. And then I say assign, joint, restraints. And I want it to be everything the same as before. So first I'll unlock it. Let's put in, let's see, restrain Y, restrain Z, restrain rotation 1 and 3. That's what we would have had before, right? We also want to restrain X. That's the longitude. Okay, so it looks funny, it's a pin, but then we're going to grab that pin and move it. That's what we told it to do. It can't apply, in displacement control, it can't apply displacements unless it's grabbing the reaction. So let's save it and rerun. Everything else will be the same. So that's the difference between force control and displacement control. If you apply forces, of course you don't need a reaction, want a reaction there, otherwise it goes into the reaction. But if you're applying displacements, it's moving the reaction. And so of course it runs more slowly now because it's going nonlinear. If nothing was moving, it wasn't going nonlinear. That's why it went so fast last time. Still solved it pretty fast. So let's see what we have now. This is the displaced shape. So it is displacing, they look almost straight. Let's go back and make sure it has any cubic lines. Let's say cubic curve, see what it looks like. Yeah, it's a little different. It's at 10 seconds now. If I put my cursor here, let's say, it's about 1 foot of displacement there, so 0.999. It's not exactly 1 because we're pulling it over here. So there's exactly 1. So it did move 1 foot, which is good. If I go over here, it's probably similar. It's 0.997. So the only difference being the axial stiffness of the superstructure and some stiffness of these measurements. And that means we probably form plastic hinges at the top and bottom of these, and at the top of this column. So let's look at that. Display, show hinge results. So you can see this one formed as I'm moving across. There's the plastic moment, and then as I go across, you can see it's, once we get onto this point, this is the rotation. It's formed a plastic hinge, so this is moment versus rotation. And you get all the way up to here, 15 times 10 to the minus 3. Or you can put on, let's see, there's the backbone curve that I gave it. So, let's see. Okay, so these different points here, this, as I move in the cursor, you can see my point moving around. That's showing that at least what we gave it, this is the plastic rotation capacity, so it has a lot more displacement capacity than the 1 foot, because at least this hinge only went out that far. Let's look at another hinge. And these are for the different members. Remember we had member 26, 29, 30, 30. Look at this one. So this one's going in the opposite direction, and then it's also not at the end. It's only gone this far in the plastic rotation. It goes this far before it fails, based on what I told it. This one's even smaller rotation. These are all the plastic hinges. There are 2 on each column, except for the last one has 1. And then the last one. Okay, let's plot the force versus displacement. So the way we'll do this is, we have the displacement here. Let's see what joint this is. I'll click on this. This is joint number 10. So I'll say display show plot function, define plot function, go to joints, add plot function, joint 10, and displace in the x. Of course, this is going to be a straight line, right? Because we told it what to do, and that's what it should have done. But we're going to plot that versus something else that will ultimately give us some hysteretic plots. Say OK. So let's just make sure that looks good. Double click it, bring it over here. It's joint 10, displacement versus time. It's just what we expected. So it starts here at 0, 0. This is time on the horizontal axis, and this displacement on the vertical. At 10 seconds, we're at 1 foot. So the structure moved over 1 foot at the end of 10 seconds. Is that clear? Now let's plot the base shear. So that's summing, if you think about it, the shear at the bottom of each column is, once the plastic hinges have formed, is plastic moment at the top plus the plastic moment at the bottom divided by the length based on statics, okay? And so that's true for each of the columns. If you sum all those base shears together for each column, you get the total base shear in the structure. And then what we should be able to do is plot, if you tested this, imagine in a large structural testing laboratory, you'd be applying this force we're pulling on it. That force versus the total, that's equal to the base shear, the force we're applying. That versus the displacement. So we have, again, we're going to go back to display, show plot functions, find plot functions. Now, add base functions. You see that? So add plot function and say base shear in the x direction. That's all I want. Okay. Let's move this over, and here's base shear. And this should look nonlinear versus time because the plastic hinges form. Okay, so that looks weird, right? It's vibrating. You see that? Let's plot base shear versus, what was the joint we just got, Sam?
10.
Yes?
Yeah.
Yeah. Okay. Versus, so it's force versus 10. All right, something is, let's see, we're in kips. Actually, I'm looking at this. At first, I was thinking that it's going through 0, but it's not. It's vibrating. See that? And then it's going. It's coming about this point here, which is 0.15 times 10 to the 3, which is 150 kips. What should it be? Something's funny there, but let's calculate it. What's the? I don't remember the length of the columns. You guys have it written down? I don't have it written. Well, I guess you could do it this way. That is 0, and there's 60. Okay, so you guys do some calculations for me, okay? I want you to give me 2 times the plastic moment. I think we have the same moment capacity for all the hinges, right? So 2 times the moment divided by 60. Give me that. That's the base shear of one column. The moment was
5,000.
5,000. Okay. So that's 167 kips for one column, right? And then the other one, the length is 80. Okay, so that's 10,000 divided by 80. Plus, 96 says 292. And then this one, you have a pin at one end and a plastic hinge at the other. So it's just 1 of the MCP divided by the height. And this height is 50, so it's 5,000 divided by 50. So the total should be about 392 kips, right? That's what the base shear should be. See what it says. Okay, so that's not correct. Let's troubleshoot. Oh. Let's look at the shear in this member. This is 26. It's already here, so let's bring this over. So that looks a lot better, right? It's not vibrating back and forth. Something about the base shear, the SAP's giving us is not correct. Because here's one column, for example. What you could do is save this to, you say file, print table to a file, and it saves it as a text file. You could bring it into Excel, and then you could do the same thing for each of the 3 columns, add them together, and that gives you the total base shear. Right? That's what it should be. We can try something else in a second. So anyway, this looks correct to me. Oh, I'm sorry, that's moment, but that's not shear. That was the right moment. Okay, we're gonna have to define a new one so based on that moment plot, it should be right. So this is add frame forces for joint frame 26, and we say shear 2-2, right? So there, again, like I said, it's not vibrating back and forth like the total base shear was. So this is, that's what we calculated, right? 160 something kips in the first column. So that looks good to me. Let's look at the next one. Let's calculate this one, which is 30. Base shear. And that's about 120 something. Is that what we had? So that looks reasonable. So it's forming 2 plastic hinges. And then that's its limit. And then finally, what did we get for this third column?
100.
What was it? 100, right? And that's 34. Okay, so it gets above 100 because we have a slope to the moment rotation diagram. So the 2 plastic hinges form, and then it picks up a little more load as the plastic hinges rotate, the way we defined it. If we go back, let's go look at that. Define section hinges, modify, see the slope there? So that's why it's going above our calculated. At this point, if they both formed at this point, it would be exactly what we have. And we could change that by changing this to, instead of 1.1, you could put 1.01 or something, so it'd be almost 0 slope. Okay, so let's try, since SAP is not giving us what we want, let's take the results to Excel and then see if we can plot the force versus displacement, because I believe the shear in each column is correct. So, let's go to display, show plot function. I'm going to bring all of them in. I don't remember what they were called anymore. 26 something. Yeah. And what else?
31.
30-1. What else?
34.
And that's all 3 of the columns, right? We have 3 columns. Okay, let's see if it looks reasonable. Oh, So it's interesting, it's the force versus displacement for each column, right? And so, because each one's going through the same top displacement approximately, so that's what you're seeing here. And you can see these have a similar stiffness, and this one is stiffer, right? Stiffness is force over displacement, so you're seeing that on this plot. So since they're all going through the same displacement, we should be able to save this file, and then over to Excel and just save the sum of the three forces, and then we could, that's the force for the whole frame versus the displacement of the frame. Okay, so file, print table to file, force, displacement, frame. Okay, and we'll go and open this in Excel, see what we can do. Oh. And there it is, right? So, say next. Space, I think. There it is. So, there's the time. This got kind of manipulated and messed up when we copied it over, but I'm trying to figure out why we're looking at 4 columns of data. Anyone have any input here? Oh, that's the displacement. I see. And then these are the forces, right? Okay, so let's say force total. Actually, better yet, let's say base shear. If SAP's not giving us the right base shear, we'll figure it out. Okay, so this just should equal sum of this, no, this. Could have just said that plus that plus that, if everything just as easy like that. Okay, then I'm going to do this. Okay, that should be it. All I did, the reason I copied this down was so that I would know the length of it. I wouldn't have to look. So that should be it, right? This is the displacement, and this is the force. Then we want to create a graph. Is that similar? It was like 390 kips, right?
392, yeah.
What's that?
I think it was 392, yeah.
Oh, that's funny. This is a little less. Okay. Insert. XY scatter. Move its own chart. It's not bad. Okay, so this is the idea. This is the monotonic, and we were able to copy the base shears of each column over and sum them and get the total force versus displacement of our frame. There's one other possibility I didn't try. I don't know if it will work, but we could plot the reaction here, the force at the point, rather than summing these. You think that will work? It is a reaction point. We're pulling on it. Let's try that. So what joint was this? 10? So let's try that. Maybe we didn't have to do all that. It should be the same, or approximate. Display, show plot functions. Define plot function. Now you go to joints. See that? And then add plot function. We say joint 10. And see this? It says reaction here. Small wording. And then F1 is in the X direction. All right, let's see what this. Let's get rid of all these guys. And let's put this versus See, it's doing that weird vibrating thing. That's where the base shear is getting that from. Although this value is different. This is approaching 600 kips, right? It's not the correct result, so there's something wrong here. So anyway, if you're doing this, if I ask this, I would sum the base shears of the columns, okay, because that's clearly correct. Get out of there. Okay, so we managed, we got around the little quirks in SAP, and we have a force displacement plotter that's reasonable for the frame. Now let's load it. That was monotonic loading. Let's cycle it and see what the hysteretic plot looks like. We're going to do the same procedure to pull out the proper results. So let's go back to SAP. And the only thing we have to change is the way we're loading it. Define, function, time history. Okay, what did we call it? Full time history. So right now we're loading it monotonically. Instead we're going to do it cyclically. Let's go look at this. See how it looks like things have gone fully nonlinear at about 0.2 feet, right? So nothing much will happen if we go below that. It'll be linear elastic, and then if we go further, it'll start cycling. So let's unlock this. Click here. And say define. Go back to functions again. Time history. Pull time history. Now we're going to change it. So at 10 seconds, let's go to 0.5. And then modify. And then change this to 20 seconds. We go to minus 0.5. So we're cycling now. So this is showing time versus displacement, but then the force displacement should reverse, so you should be able to apply hysteretic behavior. So 0.5, no, let's delete that one. Okay, that looks better. 30 seconds, okay, I'm going to control out 40 seconds. We'll go to 1, add 60 seconds, that's after a minute of running time, will be a minus 1. At 100 seconds, we're going to be at 1.5 feet. 140 seconds, minus 1.5. And then at 220, I'll go to 2. And at 300, that is 0. That's the displacement pattern we're going to follow. Okay? So, say okay. Now we got to go back to the load case, make sure it looks reasonable. The only thing we're going to have to change, so we're saying use pull time history, and all we did was change pull time history. We're still saying scale factor is 1, so 1 is 1 foot. When we go to 2 or 3, it's 3 feet. Right, so 1 to 1. And we have to change this. Right? It's every 0.1, and what should it be? 300? How many seconds are we going? Oh, so it has to be 3,000. So we'll see how this works. Cyclic, even what's called, this is quasi-static analysis, but cyclic is always, it's a lot more increments than monotonic, as you're going. out, back, out, back. Start talking about what else I've been